Hi everyone, today I'm going to be describing how to derive a formula that will let us know the max angular velocity that we can reach before a liquid in a cylindrical cup will spill over the edge. So up here I have two diagrams. This is our stationary cylinder without any angular velocity. We have a liquid with a height big R as well as the radius from the center of the cup to the outside. We're also calling that big R the same. And then we're calling the distance from the top of the cup, or the top of the cylinder to the bottom of the cylinder, big H. And over here is a diagram of what the liquid would look like once it starts to rotate. It will obtain this parabolic shape, and eventually once it is spun fast enough, the liquid will flow over the edge of the cup. So to start, what we know is that the change in pressure over the change in the radius is equal to the density times omega squared, this is our angular velocity, times the radius. So once we have this, we can rearrange the equation and integrate. So we'll have the integration from 0 to p of dp is equal to, we can pull the rho and the omega squared out front. Multiply that by the integral from 0 to r of r dr. So an issue we might run into here is that these two p's are not the same and these two r's are not the same. So what we're going to do, we're just going to make it r prime and p prime just to avoid any confusion. So once we solve for this, we get p is equal to rho omega squared times the radius squared all over 2. Okay? So I'm not going to go back up to this diagram. We're going to call some distance between a point on the parabolic shape with relation to the vertex. We're going to call this distance little h. We're going to call the center of the cylinder, we're going to call that 0. Some point in between the center and the very edge of the cylinder, we're going to call little r, just stands for radius, and we're going to call the very edge big R. That's the full radius of the cylinder. So we can solve for h at some radius r. We can say h sub r is now equal to little r squared times omega squared over 2g. And then when the radius is equal to the full radius of the cylinder, we can say that h sub r, when it's equal to big R, is equal to big R squared instead of little r squared times omega squared over 2g. Okay? So once we have that, I'm just going to redraw the diagram down here. Draw our other diagram. So I'm drawing a dashed line at the very bottom of the parabolic shape, and I'm going to continue it into the stationary one. So what you can see from here is that since no liquid has been lost or gained in either of these systems, the area under the dashed line here will be equal to the area under the dashed line in this cylinder, and therefore the area under the parabolic shape and above the dashed line will be equal to the area above the dashed line in this cylinder and underneath the solid line. So I'm going to call the distance from the dashed line to the solid line, I'm going to call that d here. So from here we can look at these two and say that pi times the radius squared times our distance d is equal to the volume of our little parabolic shape there. So eventually we're going to need to integrate to solve for the volume. If you notice, our big R minus our distance d plus our height h, little h, when the radius is equal to the full radius, that is going to equal the total height of our container. So I'm going to cut it here and clear up the board, and I will continue from there. Okay, so we're back with our equation that we just obtained. It's now at the top. And we also have this new diagram. This diagram represents the top portion of the cylinder that is being rotated, just a parabolic shape. And now I have sliced it into what looks like multiple rectangles. We're going to call one of these rectangles dr. Dr just depends on how thick you want to make your slices. So this is a side view of it. If it were to be from the top, it would kind of be this donut shape, I guess you could say. So from here, we are going to find our differential volume, dV. We are going to say our differential volume is going to equal to little h times 2 pi times radius times dr. Okay? So now from here, we can say that the volume is equal to the integration from 0 to volume of the liquid times dV is equal to, we can take the 2 pi out front, the integral from 0 to big R of h, which is our height, with relation to some radius r. We're going to multiply this by the same radius that we use for h, multiply all that by dr. So when we do this and we make some substitutions, we get the volume is equal to 2 pi omega squared over g, or 2g, times the integral from 0 to r of r cubed dr. So once we solve this and we make some cancellations, we get the volume is equal to omega squared times pi over g, all times big R to the 4th over 4. So now from here, as you saw earlier, we can say that this volume, which is what we just found here, is equal to, so we have our pi r squared times d from earlier. We're going to set it equal to this. So we get it's equal to omega squared pi over g times r to the 4th over 4. Okay? So now from here, we're just going to solve for d. So eventually we can plug into this equation. So we get d is equal to, i's cancel out, and those r's will cancel out. So we have omega squared big R squared over 4g. So now we are going to go back and plug in what we have into this equation. So when we do this, we get r minus omega squared r squared over 4g. And if you remember from earlier, h, when you have the full radius of the cylinder, is equal to omega squared r squared over 2g. And all that is going to be equal to the height of the cylinder. So from here, all there is to do left is to solve for omega. So to start, we are going to have h minus r is equal to omega squared r squared over 4g. From here, we get omega squared is equal to 4g times h minus r all over r squared. And then when we take the square root of omega, we get omega is equal to 2 times the square root of g h minus r. All of that is going to be over big R. So what we just solved for was assuming that our radius of the cylinder is equal to the original height of the fluid within the cylinder, so assuming these two are the same, we have omega is equal to 2 times the square root of g, our gravitational constant, times the height of the cylinder minus the radius of the cylinder, all over the radius of the cylinder. So that will let you know when the how fast you can rotate the cup before, or the cylinder before the liquid spills over the edge. Thank you for watching.